then we'll call it a wrap up on instability, hydrodynamic instability. Okay. So in the last lecture we were looking at the linearized governing equations. So what were our linearized equations? So if we have perturbations, so perturbed variables are, or perturbed fields, they were, so we were writing phi1 is, let us say, u1x plus epsilon phi1 prime, phi2 is u2x plus epsilon phi2 prime, right? And then so governing equation for phi1 prime and phi2 prime were the same as for phi1 because these are anyways linear. Okay, so which symbol? Huh? Here sigma is 0. So we were considering the case for no surface tension, and we were ignoring gravity also. Okay, so there can be different combinations that you can play around with, where you can add surface tension, you can make density same, you can remove surface tension, add gravity, and so on and so forth. If you have velocity difference, all of those combinations will be called Kelvin-Helmholtz instability. Okay, so if you have a velocity difference, that is the key thing for Kelvin-Helmholtz. And then we were writing that y, had we taken y or z in the vertical? Y only. So we were looking at 2D problem only, right? Yeah. So y was, so y equals epsilon c prime x comma t. This is our perturbed interface. So this is the perturbed interface. Okay. And then our governing equations. So linearized equations, what were they? So let us say interface, linearized interface conditions, what were they? So we had dynamic interface condition, what was it? What did we derive? From dynamic interface condition, what did we derive? So we have P1 equals P2 always. Okay, from P1 equals P2, so you have P1 plus P1 by rho 1 plus U1 square by 2 equals some C1, and P2 by rho 2 plus U2 square by 2 equals some C2, and P1 equals P2. So this you obtain when you apply the Bernoulli's equation at the base state. These are base state variables. Okay, so you apply the Bernoulli's equation at the base state, and that's how you evaluate these constants, where these constants are basically the constants. So if you have del phi 1 comma 2 plus, okay, that's how we wrote these constants as. So they will be obviously in general case they will be like this. Okay, so what were our linearized dynamic boundary condition when we put that P1 plus epsilon P1 prime, P2 plus epsilon P2 prime, and then we linearized? What did we get? Huh? Rho 1 del P1 prime by del T plus U1, yeah, same thing, right? These are all, this is your linearized dynamic interface condition. So this is applied at y equal to 0. Okay, you apply obviously the dynamic interface condition at y equal to epsilon c prime, but then you use the Taylor expansion and apply it at y equal to 0 at the in the linear approximation. And then what is the kinematic interface condition? What do we get from kinematic interface condition? Huh? Del c prime by del t equals del phi 1, okay, del c prime by del x, right, which is equal to u2 del c prime by del x. Okay, this expression is essentially the normal velocity, linearized normal velocity. Okay, that's why both of them are equal, and it makes sense also for del c prime by del t to be equal to normal velocity. Okay. So then we were substituting our normal mode assumption. So looking at our normal mode assumption, so first we were writing that p1 comma 2 prime is p1 comma 2 hat. So this is a function of x, y, t. So this will be now k y omega e to the power I kx minus omega t dk d omega. Okay, minus infinity. So these are our normal modes for velocity potential. Okay, these are our normal modes for velocity potential, and then when you substitute them in governing equation for phi1 prime and phi2 prime, you get d2 phi1 hat by dy square equals k square phi1 hat, and same thing for phi2 hat. Okay, basically. So phi1 hat was a e to the power ky plus b e to the power minus ky, and phi2 hat is c e to the power ky plus d e to the power minus ky. So phi1 hat is at the top. So for y tends to infinity, for it to be bounded, a equals 0. Okay, and for phi2 hat to be bounded for y tends to minus infinity, d has to be 0. Okay, so effectively phi1 hat is simply a b e to the power minus ky, and phi2 hat is simply c e to the power ky. Okay, let us substitute that in our kinematic and dynamic conditions. So from kinematic, before we substitute in kinematic condition, we know c prime, which is x comma t, a function of x comma t. The normal mode assumption for c prime is going to look like this. Okay. So of course it's a function of k and omega, but for a fixed k and omega, it is a constant. Okay, it is not a function of y. So this is one mistake that most of you have done in your last quiz, latest quiz. When you substitute the perturbations normal modes, this is the value of y. It can't be a function of y. It is the value of y at the interface. Okay. So you can't write the here. You can't write c hat as a function of y. Okay. So once you have this and phi1 hat, phi2 hat, let's substitute here in the normal mode in the kinematic interface condition. We get minus I omega c hat equals I k u1 c hat minus what is del. So this is also applied at y equal to 0. Okay, this is also at y equal to 0. So what is del phi1 prime by del y? It is minus kb e to the power minus ky, and then you substitute y equal to 0. So minus of minus kb, and this is also equal to the second one. For that, derivative will be k times c. Okay, these are the two equations that you get. So remember, our arbitrary constants are this b, c, and this c hat. Okay, you have effectively two equations, and as you will see, one of the arbitrary constant will remain as it is and rest will be cancelling out. So we can substitute all of them in one particular arbitrary constant. So let us look at the dynamic conditions. So rho 1 del phi1 prime by del t, so minus I omega phi1 hat. So phi1 hat is b e to the power minus ky. This is also applied at y equal to 0. So I am just going to directly write b, and then a plus I k u1 del phi, so phi1 hat again b equals rho 2, same thing, c plus I k u2 c. Okay, so using this we can substitute for B and C in terms of C hat. C hat is arbitrary in the sense that C hat is, if you look at C hat is the amplitude of this perturbation that you have given. Okay, you are not solving for growth rate depending on the amplitude of perturbation. The growth rate is a growth rate. C hat is arbitrary in that sense. As long as you are working in the linear regime, as long as you make the assumption that the amplitude of perturbation, that C prime is of order 1, so that epsilon C prime is much smaller than 1, as long as that is holding, our growth rates are going to be independent of its value. It is not. It is, you can look at it the same way, like phi 1 hat you substitute here, it's not so different also. Okay, so from here you get that B is minus of I omega plus, why would someone call me at this time, minus of I omega and then a I k u1 C hat over k. Okay, and so we can write it as minus of I omega by k plus u1 C hat. And for C, what do we get? For capital C, what do we get? So we bring that here. So we'll have a I of omega by k plus u2 times C hat. So let's substitute them here. So rho 1 times I k u1 minus I omega times a B, which is minus I omega by k plus u1 equals rho 2 I k u2 minus I omega times C, which is I omega by k plus u2. Okay, we are getting close to solving for the growth rates for omega basically. So we can take I here also common. So you take I common, multiplies, gets minus 1, you have minus already. So you get rho 1 k u1 minus omega plus k u1. So I can multiply the whole equation by k effectively. Okay, so that we have same things appearing. And then here you have a I common, so you'll get a minus of rho 2 k u2 minus omega and then a k u2 plus omega. Okay, so let's divide this by rho 1. Okay, notice that I had a C hat in both of them. Okay, notice that C hat was there in both of them. For a non-trivial solution, we are trying to find what are these omega. Okay, if you say that okay, this equation is satisfied when C hat is equal to 0, yes, you are right, but then I mean you are solving for unperturbed state basically. Okay, so here what do we get? K u1 square minus omega square equals minus rho 2 by rho 1 k u2 square minus omega square. Is this right? Hmm? There is no omega term. Let me see carefully. There should have been an omega term, I think. It should have been basically, this should have ended up to be a quadratic. I hope I didn't screw up minus signs. Are we sure of this? Are we sure of the kinematic condition? So we have y minus epsilon c prime is constant. Let's say this is f. So df by dt equals 0. We have minus del c prime over del t plus a u dot grad of this. So plus a capital U plus epsilon u primes I cap dot grad of y minus epsilon c prime equals 0. So minus del c prime over del t, then epsilon. Okay, this is my rough work. Plus capital U del by del x of this, so minus del c prime by del x. Should it be a minus sign here, no? Minus u1 del c prime by del x. Go through the algebra properly. So this is the correct expression. But now the question is, I should end up with the real root here as well. This should be a whole square. So del phi prime by del y, which is minus bk. So minus bk equals minus I omega c prime, c hat, and then a plus of I k capital U1. And then from here, we will get ck equals minus I omega c hat plus here also we'll have c hat, and then a plus of I k u2 c hat. Okay, so b is minus of, so b is what, minus of I u1 minus omega by k, right, c hat. So there are two minus signs, and then you have a c which is I of u2 minus omega by k, sorry, omega by k c hat. Okay, this thing now seems to make sense, because now when we substitute in the dynamic condition, rho 1 minus I omega p1 hat, which is b e to the power minus ky, so just b at y equal to 0, and then a u1 del phi 1 prime by del x. So I k u1 again b equals rho 2 minus I omega capital C plus I k u2 times capital C. Okay, what was wrong in the last derivation? I think I screwed up the signs here or here. Where were the signs wrong? So kinematic, due to this change, there is a sign, right? There's a sign reversal. So do you have so that's the, so that's the regular intuition. After doing this a couple of times, you will build that this. So whenever you have del by del t, you are replacing it with minus I omega. Whenever you have del by del x, you are replacing it with I k. Okay, these two will be added because you have some convection. Okay, so you should technically always have minus I omega plus u1 ik multiplying. Okay, you should never have the signs reversed in between them. Basically minus I omega minus u1 ik makes no sense basically. Okay, so that's why you should, I mean, these are like checks which you can make in between your algebra to make sure what you're doing is correct. So rho 1 I k u1 minus I omega times b, which is minus I u1 minus omega by k c hat equals rho 2 I k u2 minus I omega times capital C, which is I times u2 minus omega by k c hat. So for a non-trivial solution, when c hat is not 0, what do we get? So let's take I here. So this becomes rho 1 k u1 or let's multiply the whole equation with k also. So k u1 minus omega whole square equals minus of rho 2 k u2 minus omega whole square. Okay. So this is what you will get. So let us take this rho 1 here, k u1 square plus omega square minus 2 omega k u1 equals minus rho 2 by rho 1 times k u2 square plus omega square minus 2 omega. Okay. So what is the quadratic that we end up with? 1 plus rho 2 by rho 1 omega square minus 2 omega k u1. So this is plus becomes minus. So u1 plus rho 2 by rho 1 times u2, and then a plus k u1 square whole square minus rho 2 by plus rho 2 by rho 1 k u2 whole square equals 0. So we can divide this whole thing. So let's first multiply it with rho 1 to get rid of this denominator. Okay, let's multiply it with rho 1 and let's divide it by rho 1 plus rho 2. So what do we get? Plus a rho 1 k u1 k square u1 square plus rho 2 k square u2 square by rho 1 plus rho 2. So this is our final equation for omega, okay, for this case. Now a couple of points here to make. You ended up with an algebraic equation for omega, okay. You ended up with an algebraic equation for omega. This will not always be the case, okay. If you do these derivations multiple times, or if you just look at our Sommerfeld equation derivation, we did not end up with a algebraic equation for omega. We ended up with a differential equation where omega was were the eigenvalues, okay. So this is a very, this is a, let's say this is a very good situation in these kind of models or in these kind of model flows, which are also called surface coupled models. Okay, surface coupled models of instability. If you recall our demonstration of Kelvin-Helmholtz, so we are doing this in an inviscid flow approximation, but that doesn't mean that actual shear flows that you will get will be inviscid in nature. Okay, in our demonstration what we had was there was a plate here, and then the flow was coming at a greater speed at the top and smaller speed at the bottom. So you can expect that in the laminar regime the flow profile will be something like this. Okay, there will be a short region where the flow will smoothly transition from from larger velocity to small velocity, because in reality there is no zero viscosity. We are making things in the limit of zero viscosity, we are analyzing things in the limit of zero viscosity, but that is not in reality. So in reality you will have a thin region, okay, or a thin interface which is of not zero thickness, it has some thickness but small, okay. And so if you end up doing that analysis, you will end up with a equation like Sommerfeld equation. You will end up with an equation where you don't have a nice algebraic relation for omega, you will have a differential algebraic differential eigenvalue problem, just like your Sommerfeld equation. These surface coupled models are further idealization of these kind of things. Okay, what we are saying is, okay, forget about this thin region where velocity is continuously and smoothly transitioning. Let me do the analysis in the limit of that region going to infinitesimally small thick region. Okay, so the moment you consider a sharp interface, that's when you have so called surface coupled problems. In all surface coupled problems you will see that you end up with a nice algebraic equation for omega, okay, and you can solve that, and you can solve for the stability bounds, okay. only one or two cases will be there where you can form the differential eigenvalue problem and still solve. Okay, not a lot of cases are there. So from here we can solve for omega. What kind of omega do we need for instability? We need imaginary values of omega. Okay, if you look at our normal mode assumption, this omega is something like a frequency. If you end up with a real value of omega, that's just frequency. That just means there are waves that are propagating. This kx minus omega t type of solutions, these are wave solutions. Okay. So if you get a real part of omega, if you get only real omega, you are just wave propagating with maintaining its amplitude. But the moment you have omega that has a real and an imaginary part, what you get is that this wave is not just propagating. Okay, the wave will not just propagate, but it will amplify in its amplitude also. The amplitude will increase. Okay, the amplitude will increase in time. Okay, and since we are doing this in a temporal analysis regime, you will see that as the wave propagates in x, over all x locations the amplitude increases. Okay, so this is a case where you are trying to do a temporal analysis of a convective instability, because you do get convected modes, you do get modes that are traveling in x. Okay, if you look at your fluid mechanics films, which I have linked in the on the website, also given the link, so you will see that a very nice case of this, which is surface coupled Rayleigh-Taylor instability. In Rayleigh-Taylor, we had a density gradient, or due to a temperature gradient, let us say. A very nice surface coupled example of that is, okay, just a heavier fluid with rho 1 greater than rho 2 resting on top of a lighter fluid, no u1 and u2. So that's not a Kelvin-Helmholtz case anymore. There is no u1 and u2. Okay, in that case you will just see in a moment that if there are no u1 and u2, the modes will be stationary. The amplitude will grow in time, but there will not be any traveling of the modes. Okay, so let us look at the roots of this equation. What are the roots that you get? So you will simply get minus, so omega will be, what will be omega? So k times rho 1 u1 plus rho 2 u2 by rho 1 plus rho 2 plus minus square root of, so b square minus 4ac. B square also has a 4, this also has a 4, there is a denominator 2, so let us forget about that. So then we have k times rho 1 u1 plus rho 2 u2 by rho 1 plus rho 2 whole square, k square also, minus 4ac of this. So minus k square rho 1 u1 square plus rho 2 u2 square by rho 1 plus rho 2. What do we get when you simplify this? So let's take k outside. What do we get here? So we have rho 1 u1 plus rho 2 u2 whole square minus of rho 1 plus rho 2 times rho 1 u1 square plus rho 2 u2 square by rho 1 plus rho 2 square root in the numerator, and then a plus minus of k and this guy. So what can you say about the top expression? So rho 1 u1 square will cancel, rho 2 u2 whole square will cancel, and then you will be left with 2 times rho 1 rho 2 u1 u2 minus of rho 1 rho 2 u2 square minus of rho 1 rho 2 u1 square. Okay, at the top you will be left with this. So what is our final expression for omega? K times rho 1 u1 plus rho 2 u2 by rho 1 plus rho 2 plus minus k by rho 1 plus rho 2. What do we have here? Square root of, so let us say square root of rho 1 rho 2, and then what do we end up here? Minus of u1 minus of u1 minus u2 whole square. Minus of u1 minus u2 whole square. What is that? What is the square root of that? I times k mod of u1 minus u2. Right? You will end up with, so this will be basically rho 1 rho 2 times u1 minus u2 whole square. Okay, with a minus sign. So, what is the square root of minus of u1 minus u2 whole square? u1 minus u2 whole square is always greater than equal to 0. You are taking a minus of that quantity and then taking a square root. So, minus of I, so there will be a I because of square root minus 1 and a mod u1 minus u2. So, now you see the expression of omega. So, if you have this expression of omega, you can interpret it more physically if you have an expression for omega by k. Okay. This omega by k we call it as c, which is the, which is which velocity for waves? Wave velocity, technically phase speed. Okay. There is a group velocity also d omega by dk. You can call it as cg, which is the group speed. Okay. So, omega by k is simply equal to rho 1 u1 plus rho 2 u2 by rho 1 plus rho 2 plus minus square root of rho 1 rho 2 by rho 1 plus rho 2 mod of u1 minus u2 times I. Okay, and now if you reconcile this with our normal mode assumptions, what did we have for normal mode assumptions? So, let us say P1 prime, P2 prime, C prime, we wrote all of these as P hat 1, P2 hat, C hat, e to the power I kx minus omega t. Okay, and then there were integrals dk d omega. So, kx minus omega t, you can take the k outside and write it as x minus ct. Okay, and now this notion of omega by k being a speed becomes clearer. Okay, if you have a, let us say if you have a function of f and f of x minus ct basically means that your coordinate axis is traveling to the left with a speed c. So, if the coordinate axis is fixed, then you are looking at the wave or perturbation that is traveling to the right with c. Okay, that is what this f of x minus ct, and so this is what you have. And now you see that the real part of this omega by k gives you the speed of at which the waves travel, which makes sense also. If you have rho 1 and rho 2 same, what is the speed? u1 plus u2 by 2, which is something you would have said very intuitively also if I had given you the problem of a sharp jump in velocity, flow velocity. You have a flow with u1 speed, flow with u2 speed, assume inviscid, what is the speed of these perturbations in the linear regime? Intuitively you will say, oh, just take an average. Not wrong. Okay. What is the growth rate? Growth rate is directly proportional to your u1 minus u2 difference. If you do not have a difference, if you have this kind of a problem with u1 equal to u2, makes no difference. There is no growth rate basically. Okay. The growth rate is directly proportional to mod of u1 minus u2. I hope it is clear why the imaginary part of omega by k is a growth rate. Okay, because when you substitute this here, you will get I k times that ct, and if this is imaginary, there is a plus and a minus imaginary, one of them will give you exponentially growing solution in time. So, what is the real part physically? Wave speed. Wave speed. Real part is the wave speed. And so, if we could in our demonstration, if we could measure somehow, if you could change and measure the velocity differences between the two flow streams, we could have plotted this growth rate, we could have looked at the growth rate in x, and we could have plotted it versus u1 minus u2, and you would have seen that as I increase the flow speed difference, the growth rate increases linearly first, and then things happen. I mean, things become very difficult to measure once your growth rates are very high, because the linear regime is very small. Okay. So yeah, coordinate axis going left or wave going right. Exactly. Okay, so I was about to say that the reason why we say linear regime is very small in time or space, depending if you're doing temporal or convective, is because all of these assumptions, all of this linearization works when your perturbations are small. Assuming perturbations to be small, you're deriving a solution. Let us say in the case of unstable setup, you're deriving a solution that is exponentially growing in time. So there will come a time when the assumption ceases to exist, ceases to apply. The assumption is that perturbations are small, and from that assumption you're deriving perturbations are growing exponentially. So there'll come a time very soon when perturbations are not small, and that is when all of this linearization business fails. Okay, that is when all of this linearization business fails, and what happens is your solution, now the base state that you had, which is unstable, it is growing. The unstable solution, the unstable base state solution uh, promoting growth of perturbations. The perturbations are growing in time, and soon the linear regime ceases to hold. The linear regime, all the assumptions that we made for linear regime, they cease to hold. Okay, and usually in a lot of, not just hydrodynamic stability, in a lot of stability textbooks or stability courses or wherever you study stability, this is when non-linearities kick in. That's how they call it. Okay, in the pop language they'll call non-linearities kick in. What the hell is that supposed to mean? I don't know. Okay, but the point is that linear approximation ceases to hold. Okay, and then you have to consider higher order approximations of the governing equation, and there are very nice examples of this. Okay, there are very should I go to the detail of that example? I think I had an oscillator example that I had prepared for you guys. So in your maths courses, have you looked at stability of system of ODEs? You must have looked at system of ODEs stability, right? In maths 1 or maths 2, you must have looked at it. Huh? You have, right? Huh? CFD, what did you consider? Polynomial stability analysis. Yeah, that's discretization. That's after discretization. Okay, there's no discretization that is happening, although in essence everything is same. Okay, once you sort of take some higher courses, then you realize that even so, I mean, I don't want to be too reductive, I don't want to sound too reductive, but this is the beginning and the end of quantum physics also. Okay, so yeah, I mean, that's it. Okay, once you say your perturbations are like this, perturbations in fields are like this, that's it. You get Schrodinger's equation, you get all the nonsense. Okay, so which is sometimes joked around also, that physicists also always deal with linear equations, so they are not doing real physics. Because linearized equations, as you can see, we can solve for them analytically on board in a class. So what's the big deal about it? But don't quote me on these things. So jokes apart, let us look at an oscillator, which is a very, I mean, very uh, let's call it a popular example of an unstable oscillator. And the equation is like this. Let us say you have a dynamical equation which is this. Okay, so instead of dots, let's write it like this. Okay, you have a dynamical equation like this. So this is an example of a damped oscillator where this is your damping term. Okay, this is your damping term. So if you have seen damped oscillator solutions, you know when damping term is positive, then the solution, the any initial perturbation you give, it just decays exponentially in time. But what happens when your damping term is negative? Because for x less than 1, the damping term will be negative. Okay, so let us look at very small perturbations in x. Let us say x is some epsilon x prime. Okay, let us say x is some epsilon x prime. Basically, it's actually x naught plus x epsilon x prime, but you see that x equal to 0 is a base solution or a steady solution. Okay, when x equal to 0 is constant, these guys are 0, x equal to 0, so it's a steady solution. So what I'm saying is x is epsilon x prime. Let us substitute here and linearize. What do you get? d2 x prime by dt square minus mu 1 minus, so you'll have epsilon x prime square, epsilon square x prime square, and then another epsilon dx prime by dt plus epsilon x prime equals 0. Okay, linearize this, you can drop this term, and what will you get? d2 x prime by dt square minus mu dx prime by dt plus x prime equals 0. Substitute the normal mode assumption here, x hat e to the power I minus I omega t d omega. What will you get? Minus omega square x hat plus I omega mu x hat plus x hat equals 0. For trivial solution, for non-trivial solutions, let's take minus x hat outside, you have omega square minus I omega mu minus 1 equals 0. What are the roots of this? Omega is what? Omega is what? I mu plus minus, so what is b square minus of I mu, so that gives you minus of mu square plus 4 by 2. So omega equals I mu by 2 plus minus half of square root 4 minus mu square. So you see omega has a imaginary part. So when you substitute this here, minus of I omega, what is minus of I omega? You multiply minus sign here, you will get mu by 2 plus minus plus I by 2 square root of 4 minus mu square. Positive real part. The linear solution to this oscillator is unstable. The linearized solution of this oscillator about this base state is unstable. That means this oscillator, if it is at x equal to 0 and you give just a slight perturbation, it will start to grow exponentially. It won't just grow, it will oscillate also. Okay, and if you draw the solution in the phase space, which is, let's say, the space of x and x dot of this oscillator, you will get something like this. And then what will happen is, after some time you will see that it starts to converge to a solution that looks like this. Okay, if you were to plot this x or x dot, whichever one, versus time, you will see that they start with 0, they grow exponentially, and then they saturate at a constant amplitude. Same for x dot, it grows, there may be some delay due to the damping, okay, and then they basically saturate. So there is an exponential growth. After that exponential growth, this assumption that epsilon much less than 1, so if epsilon much less than 1, then epsilon x prime some norm is also much less than some norm of x naught, this ceases to hold. This does not hold after some time, because no matter how small epsilon you pick, there will come a time when x prime would overpower that epsilon. And in that case, what happens is you have this equation is not a very good approximation of the original solution anymore. You have to consider higher order epsilon terms, and from those you can derive, actually for this particular example you can derive what is this oscillatory solution, the nonlinear oscillatory solution. Okay, this is called a van der Pol oscillator. Okay, it has a name to it, and it's a good example of a case where you have the system as linearly unstable. The linear instability grows exponentially in time, and then it saturates to a constant amplitude oscillation. What happens is, actually, if you start with a perturbation which is outside this loop in the phase space, even that one actually comes back to here. Okay, and in these kind of cases, this non-linear solution that you have is usually called the attractor of the dynamical equations. Okay, attractor meaning that this particular solution is a stable solution. If you were to derive, so this is a steady solution that we derived. Okay, if we had an unsteady but if we had an unsteady analytical solution of this equation, okay, you substitute that and then you try to analyze what happens to perturbations on top of that. You will see that this particular solution is is a stable solution, linearly stable. So the solution is linearly stable. The equation is non-linearly stable at around this solution. Okay, what happens is that you are analyzing the solution's linear stability, that you can always do, but the solution itself is non-linear. Okay, so there are, I understand if it gets confusing to some extent, but there, I mean, these are just words. If you understand the maths of it, that you are substituting a non-linear solution and understanding its stability. Okay, its linear stability.
The reason that after a while the approximation doesn't hold any?
Because this ceases to hold, because x prime is growing exponentially in time. Okay, there will come a time when epsilon x prime is not small, and that's when your non-linearities are important. Basically, non-linearities become important. The linearized equation is not a good approximation anymore. Okay, and this is how, this is not the only one, but this is one of the major route to turbulence in fluid mechanics. Okay, you will say, okay, what is the connection between this and fluid mechanics? The connection is that when you have linearly unstable flows, the linear instability makes the perturbations, small perturbations, grow in time, and eventually you end up with a situation where they have grown so much in time that your linear solution doesn't hold anymore. You have to account for all the non-linearities that are possible, and you end up with, in most of the situations, you'll end up with a turbulent flow. Okay, so if you recall again our demonstration of Kelvin-Helmholtz, in that you saw that a very clean linear instability regime was there, and then things were chaotic. Okay, things were chaotic in a very general sense of the meaning of word chaos. In mathematics and dynamical systems, chaos has a very particular meaning which we are not going to deal with here. Okay, but in a general sense, things were chaotic, the flow was chaotic. Okay, and that is turbulent flow. Okay, but are all chaotic flows turbulent? Okay, are all chaotic flows turbulence, or rather, what is there a mathematical definition of turbulent flows? We'll look at this in our next class. So we'll get at best a 1.5 class for turbulence, so this will be mostly a qualitative discussion.